Good afternoon, everyone. My name is Hao. I'm currently a postdoc scholar at UC Berkeley Research Lab, working on large-scale distributed machine learning, algorithms, and systems. Today, in my talk, I'm going to introduce some latest development we did on introducing high-performance connective communication APIs into Ray to better support distributed machine learning workloads. I'm going to walk you through the motivation, APIs, and a few use cases about this new feature. Okay, let's get started. Whenever we program a distributed application on a distributed environment, we have to address communication, which is an essential procedure to exchange information or coordinate works between different processes. The most fundamental form of communication between two processes normally appears as send and receive operations. A sender process sends a message to a receiver process, such as this slide shows. The communication pattern is known as point-to-point communication, which should be quite familiar to Ray users. Ray has been developed to significantly reduce the complexity when realizing such communications in a distributed program. Specifically, we can use ray put and ray.get APIs. On the sender process, we put the data we want to communicate into Ray's object store by passing the data to the ray put API. On the receiver side, we pull the data from remote by passing the data's reference to the ray.get API, which will automatically trigger Ray lower layer RPC to complete the communication. However, there are many cases where a sending process may want to communicate with multiple receivers at once. A typical example is in data parallel distributed machine learning. A training process located on a GPU worker 0 derives its gradient updates on a local partition of training data and then wants to broadcast their gradients to all other peer processes on other GPUs or nodes in order to perform a coordinated update of model parameters. This pattern, called broadcast, belongs to one of the many connective communication types and is very frequently observed in almost every nowadays distributed machine learning training applications. How can we program such connective communication pattern on Ray? Theoretically, we can use multiple send and receive operations to assemble a broadcast. For examples, many ray put and ray get among different processes to achieve this broadcast communication. How about a more complex case? Let's consider ring or reduce, which is one of the most adopted connective pattern in distributed machine learning applications. So how does AllReduce work? The figure illustrates the algorithm. It constructs multiple message parsing rings across all processes, and at each step, it lets a process send a part of its data to the next worker process. Once received, every worker will reduce the received value with its local value, then start the next round of message parsing for a different subset of data. After a few rounds, all workers will have a synced copy of the reduced values. Assembling a ring or reduce connective using many P2P communication based on ray put and ray get might still be possible, but as we'll see later, it's usually programmatically cumbersome and might end up with suboptimal performance. These drawbacks motivate us to introduce a new set of high-performance connective primitives into Ray. Specifically, connective primitives consider communication patterns happening in a group of processes. To get an impression on how it works, taking the previous gradient broadcasting as an example. Instead of assembling the broadcast using many ray.get at each participant process, what we can do is to put all the processes, usually in the form of ray actors or tasks, in the same connective group, and each process in the group invokes the same connective broadcast call to start the connective communication and achieve the goal. Providing specialized APIs for each connective communication pattern is programmatically much simpler compared to assembling a complex algorithm using multiple ray.get and ray.put RPC calls. Simpler programs also means less error-prone. Another key advantage of providing specialized APIs are the ability to implement these primitives at a rather low level, which allows us to make the best use of the network hardware, such as Ethernet, InfiniBand, to provide the greatest communication performance, or to optimize for different types of computing devices, such as GPUs, and avoid many analysis overhead, as we will see next. So How does the API actually look like, and what benefits can it bring to us? Next, I'm going to walk you through the APIs by running a programming practice using the previous example, or reducing the gradients in data parallel distributed deep learning. In this case, we have many model training workers, each owning a model replica that locates on a different process. Each replica takes a part of the training data as inputs and computes a local version of the gradient updates. Once the gradients on all processes are ready, we invoke an AllReduce communication on each process to synchronize the gradient updates. What the AllReduce does is that it will communicate the local gradients of each process to all other processes and aggregate them. After this, all processes will have the aggregated gradients and can safely apply the aggregation to update their local parameters and then proceed to the next training iteration. This is a very typical distributed workload, and Ray provides convenient ways to implement this distributed logic. It's natural to express each model training worker and its training logic inside an actor, and let Ray spawn and manage many actors on a cluster. Suppose we want to launch a distributed machine learning training task on 16 GPUs spread across a 16-node cluster, each with one GPU. The Ray actor API allows us to define a GPU actor in the way shown on the right of the slide. Note that in each one of the GPU actors, we have created a GPU array self.gradients on its designated GPU at initialization. For walkthrough purpose, think of this array self.gradients as the gradients of the model parameters generated at each iteration of the training that need to be repeatedly synchronized across all actors. With the standard Ray API, communicating the gradients between GPU workers would require a series of ray.get calls and passing around the object reference across different actors. On the right side, we provide a snippet of the example code to achieve this using the original ray.get and ray.put APIs. In order for this code to work, we need to first substantially enhance the GPU worker actor class, so it has a few more methods. Here, we have introduced 3 new methods. The put gradient method simply put a gradient array into Ray's object store. The reduce gradients method does 3 steps. First, it pulls other gradients based on the remote references. Second, it performs gradient reduction. And third, it puts the reduced gradients back to the object store. The last method, the getReduceGradient method, tries to pull the reduced results using its object reference. So back to the driver code. With these 3 new methods, we first let all workers to put their gradients into object store by calling the put gradient. We then designate worker 0 as a head worker and ask it to pull the gradients generated by other workers from the object store and then reduce them, and then put the reduced results back in object store. This is done in the reduce gradient method. Finally, all other workers try to get the reduced results from object store through a few more RPC calls. Note that while this achieves AllReduce communication, it is not strictly following a ring AllReduce algorithm. In fact, implementing a ring AllReduce algorithm would be much more complex than this example. Do you spot any problem with this process? Despite the programming complexity, I want to elaborate a bit more on why this would cause some performance issue. Communicating between workers using ray.put and ray.get will require going through the Ray object store, introducing small overheads called by object serialization and deserialization, or by object movement between CPU RAM and GPU memory. Note that this overhead is incurred at every ray.get operation. Consider the fact that every connective primitive is assembled by many ray.get operations, and each primitive will be called repeatedly in an application, which is actually the case in iterative distributed machine learning training. These overheads can be significantly amplified and become unacceptable. Also of note that assembling this computing pattern from scratch makes it really difficult to utilize many optimization opportunities, such as leveraging NVLink, NVDirect, and other faster hardware-specific communication channels. In contrast, with connective communication primitives, we can simplify the code a lot and boost the performance significantly. Like most connective communication libraries, we first establish a connective group for this group of 16 GPU actors in the setup function, in which we invoke the init connective group API by passing in a few arguments such as word size, rank, and connective backend. Once the connective group is created, we can perform connective communication using the primitive. Here, we perform an in-place AllReduce over the self-dot gradient array using the connective API. To see the contrast, using a simple connective AllReduce call, we managed to reduce the gradients across 16 workers and store them in the self-gradients buffer in place. How do we achieve this? Behind the scene, we have created Python bindings over a few well-known connective communication backend, such as Nico from NVIDIA for GPU-based communication, and Glue from Facebook for CPU-based communication. We then develop high-level Python APIs using these Python bindings, and make them compatible with the ray programming patterns. That's why we can leverage a lot of off-the-shelf optimizations from these vendor-specific libraries. In the above example, we choose the Nico backend as the connective AllReduce backend, which is extremely advantageous to communicate contents between distributed GPUs compared to Ray's gRPC-based implementation, since Nico is optimized to achieve high bandwidth and low latency over PCIe and NVLink high-speed interconnects within a node, and over NVIDIA network across nodes. How do primitives perform compared to Ray RPC-based communication on connectives? Here we provide two Microbenchmarks. A more comprehensive performance report can be found in the official documentation. On the first benchmark, we compared Ray with Nico backend to Ray RPC backend on all reducing contents between two GPUs in one node. We spawn two workers, each worker owns one GPU, and the NVLink in this node is enabled. We observe that across different sizes of tensors, the Ray Nico backend is strictly better and can be 10 to 1000x faster in terms of latency. For the second benchmark, we perform AllReduce communication across 14 processes, spawned on a cluster with 7 nodes, each with 2 GPUs, so that cross-node communication is required. Still, we observe a similar speedup, ranging from 10x up to 100x lower latency. To say an end-to-end use case, we will use Spacy Ray project as the example. For the context, Spacy is a very nice library to provide various NLP features. Spacy and Ray have been collaborating a lot, and the Spacy Ray project is an extension to enable distributed training of Spacy-based ML pipeline using Ray. In Spacy and Ray, we implement a sharded parameter server by communicating gradients using the ray.get and ray.set RPC calls. When we replace the vanilla Ray APIs with the new collective API, we observe constant end-to-end speedup when training the Spacy-based NER, stands for Name Entity Recognition Pipelines, on distributed GPU clusters. So to give a summary of the results, if your applications happen to require connective communication between distributed GPUs and CPUs, we highly recommend to try these primitives, and hopefully speedup could also be observed in your application. Besides AllReduce and Nico backends, the Ray primitives API also support many other commonly used primitives, and also communication between distributed CPUs, or even communication between CPUs and GPUs, that is, different devices. This matrix reports the current status of the supported primitives and backends. Note that here, we use Glue as the default CPU backend, and Nico as the default GPU backend. It's worth noting that the scope of this project also expands a bit further beyond collective communication. It also offers API for send and receive-based point-to-point communication. In this example, on the slide, we instantiate 2 GPU actors and use send and receive primitives to conduct P2P communication. In many GPU-based applications, this might be faster than the Ray native RPC methods, because it can leverage the GPU-specific communication features. Despite the advantage of these APIs, it's also important to point out a few limitations of them. First, since the connective APIs are essentially performing out-of-band communication between actors or task processes, they do not go through Ray's object store. While we can bypass certain overheads, It also means we might not be able to enjoy certain benefits brought by the object store, such as fault tolerance. Second, the users of these APIs need to manually manage the life cycles of the connective groups they constructed, which might be an added mental overhead. Third, due to the nature of connective communication, in order to complete a connective communication within a group, the connective API has to be called by all processes exactly once. This introduces certain risk of deadlocks because one might forget to invoke the API at some participant process. To mitigate the last issue, we also introduce a declarative version of the connective APIs. Normally, the connective primitives are called in an imperative way. That is, all the participant process has to make the same connective call simultaneously to complete the group communication. Besides the deadlock risks I mentioned, this sometimes might cause certain restrictions on how users can use this API to implement their applications. With Ray's help, we explore a bit further to expose a set of more intuitive, declarative connective APIs, shown in this slide, that some users might find useful in their projects. Different from the imperative ones, the declarative API specifies the entire connective communication via a single API call by passing object reference of tensors owned by each participating process. These connective compatible object references are realized by a simplified Python object store with limited functionality compared to the normal Ray object reference. The declarative API is supposed to be called in a driver program instead of inside the act and task code. Due to time limit, I won't expand too much on this topic, but feel free to try them out and check the Ray documentations. On top of these connective primitives, we are building Ray native distributed machine learning training systems, such as parameter servers and pipeline parallel training strategies. A key advantage is that with Ray's help, they can be used to distribute very arbitrary Python-based ML code beyond TensorFlow and PyTorch, such as those written in Spacy, Think, or JAX, or even NumPy code. Stay tuned for our development on this part. So, to summarize my talk, connective communication are a really important part of distributed communication, especially in distributed machine learning. To support this communication and guarantee ease of use and performance, we provide a set of CCL library-backed connective primitive APIs on Ray. They have a few good features. For example, they are in pure Python, very easy to program and use. They support CPU and GPU arrays, and they also support transfers between CPU, GPU, and CPU to GPU. They also support many primitives, as well as P2P communications. And we provide both imperative and declarative versions of them. And in terms of performance, we observe that there is a 10 to 1000x faster than RPC-based connectives in many use cases. There is also an ongoing effort on developing generic distributed machine learning training systems on top of them. Stay tuned for more news. And if you are interested in the connectives, check it out in the link below. Thanks for attending my talk. Feel free to raise your hand if you have any question.